Welcome back to INST 314, Statistics for Information Science, with your host, Shawn Janzen. We're starting a new topic module, now going into the Z and T one-sample hypothesis testing, and this first video is just going to be talking about the basic foundations that you're going to need moving forward onto this particular module here. Now, in this particular lecture goal series, we're going to start with hypothesis testing, and we're going to compare a little bit of the Z, which is the normal, and the T distributions. So let's go ahead and get started reintroducing Z that we've covered in the previous term and how it compares to the T. Now, taking a step back, let's re-examine hypothesis testing. Hypothesis testing, we said, is when you're looking to detect significant differences. These are differences that did not occur by random chance alone, to see if the values you're obtaining in your sample are different enough from your population. And when we're talking about this in the context of Z and T tests, we're comparing two means. In this version, sample 1 module, we're looking to see if the random sample that you've obtained has a mean that compares against some defined population mean. And in future lectures, we're going to talk about the two-sample test, which is where we're comparing the means of two sample groups to each other, or rather, two variables within a sample, depending on what it is that we happen to be looking at. So generally speaking, the one sample compares against the population, where the two sample compares against two different sample groups with each other. Now, I was just saying that in the one sample, we're comparing against the population, and that goes back inside this idea that all one sample types of testing is comparing against the sample statistic you've obtained against a population parameter to see if there's a difference. Think of this like the chi-square goodness of fit that we covered previously, whereas in the chi-square goodness of fit, we were comparing distributions across a table to see if the frequencies observed were differing from the frequencies we'd expect to find in a given population. However, now that we're in the Z and T test land, we're comparing the means, not observed frequencies. So in order to do these particular one-sample testing here, we need to have a defined population. From that population, we're going to obtain the population parameter mu. So our population could be things like University of Maryland students, and the variable we could be looking at will be student grades. We're going to use an example on this in a future video. And we need certain assumptions in order to make this work. First of all, our sample has to be random and independent from that defined population. Now, of course, if it's not random and independent, you can still do testing on these, but you might not be able to have fully generalizable results, and your sample may not be as representative of your population. So these are things that are common to all statistical tests that we're going to be working on here. And so I'm just reiterating it here in the case for the one sample Z and T tests. We assume that these are going to be normally distributed, and this is according to the central limit theorem. So we had said once you have certain conditions, like your sample size is large enough, and then we can assume that the sampling distribution is going to be normally distributed. And we also have to have a dependent variable that is either interval or ratio. It has to have that numerical value to it that we can go ahead and calculate a means of it. If you have some sort of nominal or ordinal variable that cannot produce a mean, you can't do a Z or a T test. Now, I'm going to put a little asterisk on there with the ordinal component because we also have said in class that the soft rule, if you have ordinal variables with many categories, we can kind of sneak them through as if they are numerical. So just keep in mind the size of your ordinal variable, the distribution of that ordinal variable, but in general, the rule is that your dependent variable has to be interval or ratio such that you can go ahead and get a mean off of that variable. Now, if we're going to go ahead and compare the Z and the T's together, we would say that a Z test compares a sample mean to its population mean, and the probability of the observation comes from that mean. How far the data point comes from is in terms of a standard deviation from a mean. Compare that to a T test, where we're looking to see if there is a statistically significant difference between the groups with the one sample, and we're finding out if these differences in mean could have occurred by chance alone. Sample size with Z's, you have to be larger than 30. T's, they have to be smaller than 30. Sigma in a Z test, sigma is known, and in T's, sigma is not known. Both of them are approximately normally distributed, and T becomes more so when the N is large. Let's go ahead and put this into a flowchart mode. Start with your sample size. Look, is your sample size greater than 30? If it's not, you're doing a T test. If it is, then let's go ahead and ask ourselves, do we have the standard deviation of the population? If yes, then you're doing a Z test. If no, then we're going to say it depends. Now, when I say depends, this is going to be based on a few things, and the internet's going to tell you different things as well. So we're going to say, how well known is the population standard deviation. Could it be estimated? Do you have something close enough? But more importantly to the point, that when your n becomes large, the t-test approximates the z-test extremely closely. So at the end of the day, if you don't actually have the population standard deviation, just go ahead and do a t-test, and you will get results that are extremely close to what they would be for a z-test. Extremely close. The t-test is going to be your friend for most of the exercises you're going to be working on. And let's see just how different some of these are. Let's show you the formula for this. So when we're doing the one sample z and t test for the means, we're looking at z or t is equal to, in the numerator, x bar, your sample mean, minus mu, the defined population mean, divided by some standard error. Now the standard error is going to differ slightly depending if you're doing a z or a t, but they both come with the same idea. They're both doing some measure of standard deviation divided by the square root of n. And in the z, the case is standard deviation is sigma, and in t, standard deviation is s. In both cases, n is your sample size. So you can see here that these are extremely close. The only difference between them is how are we defining standard deviation, as sigma or s. And when we do the t-test, we have one little extra piece of information we need, degrees of freedom. And here, degrees of freedom are equal to n minus 1. That's your sample size minus 1. You do not have degrees of freedom with a z-test, only a t-test. And so let's go ahead and take a step back and go into a little bit of a story mode here. Let's talk about William Gossett and the tale of the student's tea. So William Gossett was a brewer for Guinness back around 1899 to 1937. And he was often concerned about the quality of beer over at Guinness. Now, brewery output at Guinness had doubled to nearly 1 billion pints between 1887 and 1914. And at the time, this person known as Thomas Case, he was Gossett's boss, was measuring the quality of hops in their batches. And these were sample sizes around 11 to 14 at a time. And he was concerned about the proportion of soft resins to hard resins that were produced in a batch. These things were being challenged at the time, and the brewers didn't quite know what it meant. So there weren't many inferential statistics at that time to help them with small samples analysis. So Gossett comes forward and says, you know what, I can work on this. He studied small sample representations and how you can use things like the malt of extra observations to be confident with the degrees of saccharin, which is the amount of sugar content in these batches. So he went and said to Guinness and Thomas Case at the time, he said, I can do these small sample analyses. Let me go ahead and work on methods that can help us produce better beer. His bosses were happy, and they said this is great. Their beer production and quality went up. But Gossett wanted to take it a little bit farther. He wanted to explore these small sample statistical testing. So he went off to UCL, which is University College London, and he worked with somebody named Carl Pearson. He is the same person that when we talk about Pearson's R later, he's the person behind Pearson's R. But anyway, he worked with Carl Pearson to work on these small samples here, and they developed what they called the law of errors, which is the math for the small samples in statistics. And this set the foundation for much of the statistical significance that we're using. So when you hear of people like Fisher and 0.05, a lot of this comes back to this set here. Now keep in mind, Guinness at this time was very happy with Gossett and how it helped Guinness's production for the quality of beer. But they didn't like the idea that Gossett was producing these small sample statistics in journals and publications for people to understand these sorts of things. They were worried that he would be publishing these sorts of secrets about Guinness, using his work there as the examples for what was being worked on. So Guinness wouldn't allow him to publish under his name, and so Gossett wrote under a pseudonym, a different name as he did these publications, taking on the name Student, which is where you hear the name Student's Tea. So if you hear Student's Tea Test, that's just an honorarium talking about William Gossett and not a particular type of tea test. Now let's look briefly here at how this looks between the Z and the T. So the blue curve is the Z standard normal distribution. And so it just follows all of the rules of the normal distribution we've covered before. The T distribution, when n is smaller than 30, looks like you took the Z distribution and you put your hand on the top of it and just smushed it down. And when you smushed it down, it blows out the sides, making it become a very squat distribution with very fat tails. And as n becomes larger, as it becomes close to 30, those tails thin out and the peak begins to rise, at which point it starts to approximate z. And as n becomes larger and larger and larger, the difference between the t distribution curve and the z distribution curve is extremely small. We're talking to 3, 4, 5, 6, and many more smaller decimal places as n, your sample size, becomes very large. And this is where we're going to go ahead and close off our lecture on the introduction to the Z and T one sample foundations, and I'll see you all in the next video where we start to explore it a little bit farther.